Okay, let's start. Welcome everyone for the afternoon of this fourth day of the Julia EO workshop. We'll now have a talk by Mr. Simon Lupemba entitled of the Dirt Observation Processing Chain. And Simon, the newest addition to the scatterometry team at EUMETSAT, contributes to the operational observation of ocean winds needed for global weather forecasts. His daily work involves using Julia to monitor and maintain processing software for the ASCAT instruments aboard the METOP satellites. Additionally, he contributes to developing software tools for the upcoming SCA instrument on the METOP second-generation satellites. Simon holds an MSc in Earth and Space Physics and Engineering from the Technical University of Denmark. His interest in Julia began during his studies in 2019. After a 2-year period of working with C on medium-sized public IT projects in Denmark, Simon eagerly embraced the chance to return to scientific computing with Julia upon joining EUMETSAT. Simon is excited about the potential to use Julia to improve the processing chain of Earth observation and wants to play a part in the realization of this potential. Thank you.
Thank you for the really nice introduction. So, I don't think that's much more to introduce. I think I'll just start the talk. To the title, I added scatterometry as an example, and that's because I work with the scatterometry instrument, and that's kind of my speciality. So the talk is going to focus on that as an example, but some of the things I present also applies to the other instrument and data sources. So first up, here's a short agenda, and I'm going to start with a quick introduction to EUMETSAT. I think that gives a better context for the presentation. Then I'm going to go through the EO, our processing chain. So it's like the data comes from the satellite and what happens before you actually download it from some data hub and use it. And then I will talk a bit about how we use Julia in my team and at EUMETSAT. And lastly, I will present my personal view on Julia for EO processing. And I say that is my personal view because I don't think EUMETSAT have any official view or thing. So, I mean, it's not the whole organization. And the conference is called Julia EO. So I thought it was also good to have like something really focused on the Earth observations part. So first introduction. EUMETSAT is an intergovernmental organization with 30 member states, mainly located in Europe. It's not the same as ESA or EU, but there's a large overlap in a lot of the member states. So therefore we also have a large amount of collaboration. But we have our own set of member states that we serve. Our primary objective is to establish, maintain, and exploit European systems of meteorological satellites. So that's meteorological satellites for weather. And then we have the further objective that is to contribute to the operational monitoring of the climate and the detection of global climate change. What this kind of means for us in practice is that we focus on meteorological satellites and long operating programs to ensure that we have stable data for the weather models and the forecast. But we do not create weather forecasters at EUMETSAT. This also means that a lot of our satellites rely on like well-tested and well-proven measurement concepts and technologies, because we're not so much a developing agency trying to make the next cutting-edge instrument. We need to have something well-proven that can work for a long time. And also a difference that's worth to noticing about these two is when we do weather data, like data for weather forecast, it is extremely important for us that we deliver it fast to the meteorological organization and to ECMWF, the European Center for Medium Range Weather Forecast. So speed is really a essence there. Whereas if we talk about the climate, it's okay that the data is old, but for the climate perspective, we also are committed to when we improve the processing software, then once a while we do a reprocessing campaign where we also reprocess and improve some of the historical data, or I mean just data that's too old to be used for weather forecast. Yeah, here's an overview of some of the European satellites ESA developed, but we have this, all the orange there, which are the meteorological satellites, which are operated by EUMETSAT, and then in the middle we have the Copernicus satellites, which is funded by the European Union, and some of them are also operated by EUMETSAT, and we maintain some of the processing for them and the ground segments. But yeah, as the slide says, ESA is involved in the development of the satellites to start with. Yeah. I just wanted to show this slide to show like some of the time frames we work with. So I'm going to talk about an instrument on the MEDOP satellites, where we have A, B, and C, and that's been up, like the first one, the MEDOP A, I think it started operations in, it was launched in 2006, and it has been decommissioned now, but we still have MEDOP B and C that are providing data. And then I'm also involved in the preparation for the next generation, so that is the MEDOP second generation, which we will launch in the coming years. And that's, as you can see from this slide, it's planned to operate into 2045. So we're planning this program for 20 years. So we're really trying to work with some long programs and long time scales. Yeah. So that's enough about EUMETSAT. Then let's dive into to the instrument I work with. This is a rendering of the ASCAT instrument on the MEDOP satellite, and maybe I just jump to the next because I think that's more fun. This is the new one, the SCAR instrument on the second generation. First of all, they look alike. So it's because they use the same measurement principle. The new instrument is just better and have a bit more capabilities, or like have more capabilities in area. But the principle is kind of the same. It has these 3 arms that extend out from the satellite, and each arm have 2 radar antennas. So the panel you can see on each side is actually an antenna for the radar, scatterometer radar. So in total we have 6 radars, and as you can see there with the people at scale, this is not a nano satellite. I mean, we're talking a big instrument that is launched. Yeah. I'm just going to show this for the measurement principle quite quickly. So why do we have these 6 antennas, you might ask? And that's because we want 3 of them to point to the left side of the satellite and the 3 others to point to the right side of the satellite. So when the satellites orbit the Earth, it tracks out 2 swaths, one on the right side and one on the left side. And in each swath, we image each pixel by the 3 different radars. So we got 3 observations, which will become important later. Yeah, And I mean, the measurement principle is a little bit the same as the SAR satellite with less processing. But as you can see, this is geared differently, and it's also because not only do we want the 3 observation, we also want a really huge swath, because for weather it's important to cover the entire Earth, and it's important to do it regularly in time. So I mean, we don't have a good spatial resolution, but the temporal resolution is quite high. Yeah, so that's why it's designed like this. And I think we had some presentations earlier where you talked about Sentinel-1 and Sentinel-2 images, where you often have the thing of not having any images over the oceans. This is not like that. We try to image everything. Yeah. Oh yeah. In the next, to understand the processing chain, it's okay to like know a little bit about the normal terms used for the different processing levels. So this is like these processing levels are normally used by NASA, ESA, and EUMETSAT, and more. I didn't go into depth if anyone else were also using them. But what we normally have is that we start with level 0 from the satellite, which is just these raw observations. So it's actually the things the analog to digital converter kind of measures in the instrument on the satellite, which is we then get down. And then we have the level 1B where we transform it to geolocate it, position it on the globe, like where's the measurements actually from, and we also do radiometrically calibrated backscatter. Yeah, I didn't write backscatter there, but radiometrically and geometrically calibrated geolocated data, and it's because I mean some of these things, these things is not only applies to the ASCAT, but also other instruments have this. So you start with the raw data, and then you do some calibration and corrections and geolocate, and then you have the level 1B, and then normally when you get to level 2, it's because you start to derive geophysical properties, to know more. How does that look? I made a small picture here, a small diagram. I think it's quite easy to understand, but we get the data down from the satellite using a ground station. It's fed into a level 1 processor, which take the level 1 data together with some auxiliary files, spit out level 1 files, and these are then disseminated, sent out in real time to meteorological services and super users that want them real time, and then they're also placed on the data store in the archive, so we save them. And then we also take it to a level 2 processor, which then process the data to level 2 products, and then we send it out. I'm actually mainly involved, and my team is with maintaining and updating the level 1 processor. So I mean, I know a bit about the rest, but that's really where I know the most. Yeah. Okay. So enough abstract concepts and slides like this. Let's try to look at a more concrete example from the ASCAT instrument. So here I've taken some level 0 data, and it's really the instrument data. So for this instrument, it comes in data records, which is you get like one data record from one antenna, and then you get one from the next antenna, one from the next antenna, then one for the next antenna. In our case, it contains antenna ID, and we also have the echo and then some noise measurement and some internal temperature measurements. And all of this is in unsigned integers of some sort, which corresponds to what the instrument actually measures, like the analog to digital converter and the onboard processing. The only like dimension we have, or like thing we have, is we have timings from the onboard clock, so internal timings. So that is what we later use to geolocate the observation and find out where it is on the Earth. But at this point, we actually only have the time of the measurement. And then, I just put some data rates. So right now for ASCAT, we have some onboard averaging, so it's not so high. And that's simply to save on the data rate, because downlink is both storage on the satellite and downlink is like a constraint. But on SCAR, the new generation, we luckily don't have any onboard averaging, so there we will get one data record down for each pulse the radar sends, and that will allow us to do more complex analysis and maybe even derive some new products. So I really look forward to get my hands on that real data once it's launched. And maybe now, I could have said it earlier, but now just going to talk a little bit about like what this big instrument is actually used for. So I mean, we send each radar antenna are used to send out a pulse, and that hits a surface, the surface of the Earth. And if the surface is flat, plane, then it's the echo is reflected away, like the signal is reflected away. But if there's roughness or anything else, part of the signal is reflected back to the satellite, and that is what we measure with the echo. And as you can see, if you go, I mean, it's a good day to understand that high winds causes waves and roughness on the ocean. So the whole principle about this, at least for the wind retrieval over the ocean, is that the stronger the winds, the more backscatter and the higher the echo is. Yeah. So level 1 processing. So what do we actually do to go from this level 0 to the level 1 data? We have the processor and we have the level 0 files, and they are, of course, really important for the processing. Those are the ones that change all the time. But to locate the, to map these unsigned integers to actually backscatter values, or like what comes back, and to apply some corrections, we need to know a lot of information about the instrument. And that we have in some auxiliary files, which is also fed in. And that is where we have the characterizations of our antenna and our gain patterns. And we also have like some of the physical things, like which way does the antenna point relative to the satellite, and things like that in the auxiliary files. And then we also get the orbit state from the satellite. So what is which orbit is it in, and we also propagate that orbit state to find out where is the satellite at the different timings that we measured our instrument. And these timings are then used to geolocate the data and find out at this, like when this measurement was taken, the satellite was at this position, and the instrument was pointing in this direction. So therefore the observation must correspond to this place on Earth. So that's kind of the process of geolocating it. This also means that, I mean, of course you don't see that in higher level products, but normally when you have something like this that is a polar orbiting satellite, or in general you have Earth observations, a lot of the observations actually have slightly different timestamps if you go into details, because it's often like one observation are taken one by one, or there's a scanning instrument on the geostationary satellite scanning the Earth to make an image. I mean, for a lot of use cases, it's nice to just have one timestamp for the entire file, but it's just sometimes good to know in reality that the time changes throughout the files, and also that once we do this mapping from time to geolocation on Earth, it doesn't end up on a regular grid to start with. Regular grids in Earth observations, that's something you get to by resampling the data. I don't think it's native to any instrument. Yeah, okay. And then I have an example. This is, I'm just going to show some full resolution data using Markey and Taylor because it's good packages. And so here I just plotted the backscatter in decibel over an area. It's like a 3-minute slice, and this is from one of the antennas, what you see. And what you see is that you have the coast, which is a bit brighter, the land, and then you have the ocean, and you have different structures on the ocean depending on the wind speeds. And if we go out a bit, then I also did like this, made a little slider, so we can see that the different antennas, if you take the same stream in the slice, the different antenna covers different parts of the globe. Yeah, so like this is some 3-minute slices from one side of the satellite, and then we have the same 3-minute slices from the other side of the satellite. Here. Yeah. So this is an example of a level 1B data where we have converted it to backscatter values. So this is in decibel. And also have geolocated it because otherwise I couldn't plot it on a map. Yeah. So let's go. Oh yeah, and I have another. So one thing we do, we have several level 1B products for ASCAT, and one of them is reduced resolution. And here we have the first was the full resolution. This is a reduced resolution, but here we have resampled the observations from each swath to overlap. So we have 3 values, 3 backscatter values for each point on in each swath. And there we have like the backscatter for the forebeam. It's the antenna beam that points slightly forward on one side, and the mid beam directly to the side, and the after beam. And I also just scaled that from in some dB and plotted that as an image to show here how that looks. But I mean, it's not easy to see what's going on based on the colors. And the thing is, if you rotate the satellite, the colors change. I mean, these colors depend on the direction of the satellite relative to the things you're imaging on the Earth. So this plot is just for to show that things are working and like how to visualize the data. But in practice, a plot like this is not so useful for anything else than debugging if something is going on with the processor. So I mean, I could use it sometimes. Yeah. Okay, so this is the level 1. How do we go to the level 2? So like one of our level 2 products, and it's mostly like, it's important for the weather models is wind and wind directions over the ocean. And actually this is not done so much directly by us as it's done by the KNMI, which is the Dutch Meteorological Service. So we have a collaboration, and it's like that with many of EUMETSAT's higher level product that we collaborate with different institutes in member states that does some of the higher level processing or maintain some of the software to do this. So this I'm going to talk about is some models from KNMI. We have a model that relates the wind speed. Yeah, we have a model that relates the wind speed and relative wind direction, and that's the wind direction relative to the antenna, and then the incidence angle to which backscatter we expect. So for a given incidence angle it's determined by like how far out in the SWOT you are, and then the relative wind direction and the wind speed. And I also have some plots to show that. So if you take all, so if you take that model I showed there and you fix the incidence angle, and then you take it for a configuration of our satellite, and then you run through different wind speed and wind directions, then it outputs like a surface like this we're shown here, which we sometimes call the wind cone. And you can see the axis is what backscatter did we expect to measure in the after beam, the mid beam, and the fore beam. So we have our three different antenna beams. We take the observations there and map them to an axis. The red dot shown here is an actual observation from the instrument. So that's actually one of the observation points from the reduced resolution product. So I just plotted it there to show that it's kind of lies on the surface. And here I made some sliders to show that the blue dot just matches the sliders here. So you can see as the wind direction change, what we would expect to observe. That's not the wind direction. As the wind direction changes, what we would expect to observe with the radar, with the instrument changes. It kind of rotates around this cone, what we would expect to see. And as we change the wind speeds, then it moves like up and down, because high wind speeds we expect like a lot of backscatter from all beams. Low wind speed we expect low backscatter for all beams. So finding the actual wind speed and wind direction can be seen a little bit like having some sort of software that moves these sliders around until the model matches the observation. So for example, in this case, it might be that we say that we expect the wind speed to be around 16 meters per second, and the direction is probably around 60 degrees relative to the mid-beam. And there's a surface inside a surface here. So it's kind of twofold. I think I have like a slice of it here, which make fitting things a bit harder. Slow here. But like this is just a slice of the cone, so it like there's some ambiguities for some special directions and things like that, but it is also not supposed to be too easy. So this is done. I wrote OSISAF here, which is the Ocean Sea Ice Satellite Application Facility. It's done by KNMI via them, but it's done by EUMETSAT partners. And they to make level 2, they estimate wind speed and direction based on the level 1 backscatter. This product for wind speed and wind direction is only done over the oceans. They also have some algorithm to kind of correct for ambiguities, and in the product they also include some quality flags and some distance to the model function to kind of show like how good the fit is. And I have an example here. Let me see. I think this example is one that matches the data I showed before. So the 3-minute slice where we have some wind speed around, and maybe I can show like here. So we have the wind fields here, and the red ones are flagged. We automatically have a flag for everything close to land that it might be affected. So I mean, and we also use a flag for really low and really high wind speed. So just because it's flagged, it can still be useful. But I don't want to spend too much on this because just before the presentation, I got the latest product over the Azores. So this is from, this was taken between 9:30 and 11 today over the island. And as you can see, we have really strong winds. I mean, I don't have any scale for the winds here, but it's quite an intense wind field. It's even, I think even some of the values in the wind field that are not near islands are just flagged just for being strong, because it's also hard for the model to fit the really strong winds. Which, I mean, this is for ASCAT. In the new instrument SCAR, which is being launched, we will be able to better resolve the high winds. Yeah, so I mean, we have really good coverage here. Maybe I skip this demo because of the time, so I also have some time to answer questions. But of course, we don't throw all the information away over land. We have some soil moisture product based on our data. I actually just show quickly. Yeah, so we have some soil moisture data because you can also see soil moisture using ASCAT. And what we see down here is probably a desert. So we don't throw the data over land away. We also use that. Yeah. So fast. Next. Yeah. So beyond level 2, I'm not an expert, but apparently we also have a level 3 product, which is the Global Sea Ice Edge. And here it's not just based on ASCAT data, it's also based on microwave radiometers. So what is done in this product is that they aggregate all the data over the polar regions for an entire day, both the ASCAT, the scatterometry data, and the microwave radiometer data. And then based on the whole combination of this data, they estimate the sea ice extent as a daily product. And with not too much confidence, I think this is like a good example of like a higher level product that, first of all, you start to diverge from the, you don't just use one sensor anymore, you use multiple sensors. It's not really in the grid that follows the satellite anymore, but you have like average over a period of time to make sure that you have a region data field. And then you also, you use information from multiple instruments, even on different satellites. Yeah, how we use Julia on my team. Julia is a niche at EUMETSAT. There's not so many that's using it. I know my team is using it. I mean, I'm using it a lot, and 2 of my colleagues are using it a lot. Some others of my colleagues are using it a bit. And then there's another team with another instrument, the infrared team, that is also using Julia. But I mean, compared to how many we are at EUMETSAT, there's a lot of people who don't know what it is, if I say it. Have no idea. Yeah. Then what I'm using it for is like, we use it for visualizing the data, monitoring of the science data, seeing everything is all right, tools for calibration, regression testing. I have some tools to compare some data, prototyping. And then lastly, Julia is not used in the operational processing chain. So so it's not there yet where the manage like the people where people feel comfortable enough to actually use it in the operational processing chains. It's for some of these also really important items for making a mission work, but like, I mean, most of these things are not time critical in the same way. Yeah, and then my personal view on Julia for Earth observations, and I mean, I must say it's my personal view because, as I said before, most people at EUMETSAT doesn't know about Julia, so they probably don't have a view on it. I see there's a lot of opportunities because what we need is high performance scientific computing, and that's what Julia is made of. The composability could improve like our that we do more reuse. I would also like that we had more open source, like that we publish some of the things, not only the tools for the users, but also some of the processing we actually do. The flexible data types is really good, and I mean it's powerful that Julia is so flexible, because sometimes we have weird things like a complex number, which is, I think we have a complex number which is 24 bits in total. So that's 12 bits for the real part and 12 bits for the imaginary part, which is, I mean, it's quite nice to have a language where it's not so hard to work with this. And yeah, then we have some challenges, clear challenges. First of all, yeah, EUMETSAT is not a general first mover. We have long operational programs. We need long stabilities. The operational chain really relies on well-tested, well-proven technologies. Everything that is called breaking changes is everyone gets scared. Awareness. People at EUMETSAT simply don't know about the language. Like, I mean, some does, but like there's also a lot that doesn't. We also have the industry uptake as a challenge, because a lot of these processing software that we're using operationally, we put out tenders for companies to bid on, and then the company delivers the software for us that we use. So we do the specification and sometimes also some prototyping. But in that scenario, it means that both the companies that are actually building some of these components and EUMETSAT should both be comfortable with the idea of using Julia in operations for this to be a success. Yeah, maturity. Again, like everything called breaking changes scares people at EUMETSAT. So and also like the tooling for doing it. It's okay that the language is flexible and there's the potential to build tooling, but of course there's like a tendency to stick with the languages where the tooling is already there. And I mean, especially if the tooling is already in-house and the expertise are already in-house, that, I mean, you can do it because you have done it before. That's sometimes easy to fall back to. And I mean, also just when you run an operational program for 20 years, you don't want to risk of jumping on a trend that just disappear, and then suddenly you cannot recruit developers or anyone that want to work with it. So there's a bit of comfort in being a part of what the larger community does. Yeah, and last thing, I also have open source versus proprietary information. It's not always the view that at open sourcing things are good things, because sometimes we also, I mean, a lot of the time we also have contracts with companies where they get to keep part of the intellectual rights when they develop software for us, and that's supposed to like help the European industry grow. But I mean, it also kind of conflicts a little bit with the whole open source idea. Yeah. The road forward. So what I hope to do, and I hope where we can go. So I hope to publish a package I made. I think it's for reading and handling the ASCAD data, because I think it's important with like an open source community like Julia, when you're part of a big organization, also to engage with it and give back, not only take. I hope to contribute to open source packages relevant for EUMETSAT. Then I hope that we're able to prove the value of Julia through non-operational tools in the organization. So we're not going straight from the operational tools, but for the prototyping and the calibration. Then keep an eye out for first movers. I'm really hoping that other organizations, our partner organizations like ECMWF or ESA, or some of them also picks up Julia, so there can be a bit of synergy. And then, I would try to just advocate for Julia inside EUMETSAT. And the last slide I have is how can you help me transform EUMETSAT to use more Julia? So first of it could be nice if engage. So we have like a lot of data up on a data platform. I mean, most of our data is freely available. So you can go there, make cool stuff with Julia and the data, and then maybe be a bit vocal about you use Julia. Because, I mean, right now I think the general view is that we have a large Python user base. So once we develop user-centric tools, it's for Python because that's what the majority of our users use. And then we have a meteorological satellite conference in Germany here in the summer, and I would love to see some Julia users there, or like some Julia relevant presentations. And there's a special early career scientist initiative if you are under 32 and have under 2 years of work experience. So that also includes if you're a PhD student and something like that. And so maybe check out the data, check out the conference, and then I hope to see more Julia users in this space. I just show quickly the data store. So here we have an example. You go to the data store, you choose ASCAD coastal winds, and then you can access the data. But you can access the data and download like a whole orbit of wind estimates and wind direction. So like just some side notes to this. Right now, this visualization of the footprint for the level 2 data, there's a bug. And I have reported it, and I think they're working on it. So if you choose an area and like download the data and it doesn't fit completely, I mean they're working on that bug. But I mean for the level 1 data it fits, and also I mean it's only the level 2 data which is in a nice NetCDF format. When you go to the level 1, we have our own binary format. That is the thing I hope to solve with the ASCAD data package. And lastly, we also have a user portal. And I mean, I don't know a lot about the user portal. You can Google it, but it got launched 2 days ago. So it's completely new. But like they're doing more to make the data more easily accessible. I think I use my time now.
You? Claro?
I know you said it earlier that this has nothing to do with you, but do you know how to become a super user?
Like super user?
Yeah.
Of what?
Of the data. You said the super users can acquire the data earlier.
Yeah, okay. So that's sometimes. So I went over it briefly in the start, but we have two different ways of accessing the data. We have the data portal, which is the easier one, I would say, and it's just made to like get some data on demand. But then we have like a lot of infrastructure to streaming out the products in near real time as soon as we process them. So they're put out, and that's called Humidcast and maybe Humidcast terrestrial. So like the Humidcast, you actually need to have like a small parable, like a small antenna, kind of like Starlink, and then you can like get it really fast. And for the terrestrial, you just use the internet. But there is, I mean, a lot of our focus is on the meteorological services, and they need to just get the data out as soon as we've processed it. And I don't know if like what it requires for private persons to sign up, but I mean, I think you can do it through a university also. Yeah.
I was also thinking on how good it represents coastal winds. Is there some kind of limitation? Have you, I mean, you or other people have done comparison with buoys that has meteorological instrumentation?
So, with the wind buoys, one of the most obvious thing is our spatial resolution. So we have, like, I mean, I think the data I showed was on a 12 by 12 kilometer grid, and when you average like the wind speeds over such a large area, you get like a significant like you get a different distribution compared to like point measurements for wind buoys. Yeah, so that's like one thing. If you like try to compare them one to one, you should like account for the resolution. The same if you compare it with anything else. Yeah, and then on the second, like if we have any known biases, and there is one known bias, and that is this is equivalent wind stress. So this is the wind, the wind movement relative to the ocean. So all ocean currents, like stable ocean currents, are going to be an error in our wind estimates. So that's one of the things. We are like actually hoping really much with the SCAR instrument and with not having the onboard processing that will be able to better correct for the ocean currents. So ocean currents is definitely one thing, and yeah, I think that's it. And of course, I mean, there's also. I think there have also been tests of like using information about significant wave height in general, like if you have larger waves to correct that are not caused by the wind. But I don't think that's a big thing. I mean, it is possible, but I mean, the bias they talk most about is the ocean currents.
Thank you very much.
Yeah.
Yeah, I found it very interesting that you mentioned this challenge for an organization like EUMETSAT that whatever software is developed there, even though we would like to have it open source, right? I mean, Julia, the idea of Julia obviously is also doing open source things, although it's on an MIT license, so you can also do a lot of other things with it. But still, I find like for a lot of these big organizations that are, I mean, EUMETSAT is like funded through some member states, so I think the organization is very similar to, for example, ECMWF. And I do understand that obviously there's a lot of money put into something that they don't necessarily want to put it right out as like MIT license, and some kind of company could run away with it and just make a bunch of money with it. But I still don't understand why these companies are so resistant to putting it under any other open source license where they can basically dictate their own terms of like, hey, you can use it if you're like an individual, but for example, it's a non-commercial license, so you can't make money with it, right? And I feel like there's really that, I think we as a community, as open source community, you really have to push for these, like this whole gray zone in between, let's say, super permissive MIT license and having everything closed source, because otherwise I feel like we always reinvent the wheel. We always do like, oh no, they have already done this, but they're not allowed to share this. And I feel these institutions are always lagging behind, and it's like, it's really frustrating.
But I couldn't agree more, but I mean, I think my view is a bit biased in that sense, because I like Julia and I like the open source. I think the big idea is at least that once the European companies develop something for EUMETSAT, then they get to keep the license and keep it so they can resell the software or like use it in some other commercial products, and thereby stimulating the European economy and the economy of the member states. And the fear is that if it's just put out, then they won't have this opportunity, and you won't get the industrial stimulation of the programs that is also part of it. So yeah, I think that's one. But I would say, like at EUMETSAT, we're controlled by the member states, and the member states have delegates in the member countries, and if a lot of the delegates at some point would say, we think you should open source more, then EUMETSAT would do it. So it's also like that. It's like, it's also, I mean, we're really I mean, we're advising the delegate, but like we're doing what the council tell us to do. So larger change in an organization like EUMETSAT could also partly and something come from the council. So find your local delegate.
Thanks for this great talk. So, in the plot that you showed, you maxed actually quite a lot of data near the coast, and it didn't obviously look wrong, the wind arrows that you showed in red. So, I'm wondering if there's some data that can actually be recovered, so that even if, so are you sure that they are bad, or are you just prudent to not to show them?
Yeah,
or to use
okay.
them?
So what I showed here, it's like I mean, I know I colored it red, so it looked bad, but I just showed any flag as red. I mean, the flags, there are individual flags, some for quality, some just for being close at land, some for being there. So I mean, I think if you look into the actual flags, you would find that some of the ones near the coast are flagged as being of good quality, like still seems to be of good quality, don't have the poor quality flag. I just, to make a fast visualization, I put all the flags together and like colored it. But I mean, if you look at the individual flags, and I mean, there's also one thing they really use is also the distance from the cone, wind cone I shown. So like if you have some contribution for the land or something in one of the beams, what you would often expect is that you get a point that does not lie on the surface of the model, and therefore that's like actually one of the main tools to really discard data.
I have another quick question, if I may. So, what does the process look like to choose a language at EUMETSAT? Can somebody use just by themselves to choose Julia or another language, or is this more group-wise or institutional-wide decision what to choose?
So it's actually like at least in my department. I mean, there's there's an advice to like kind of align with the team, and I think that's also the general approach. But there's also some freedom for the individual teams to choose their day-to-day language and what they do. There's quite a lot of I would say expert freedom for the experts to choose themselves. But as soon as it goes for the operational tools and we go for tenders, then I think, or like when it comes to deploying things in the operational pipeline, I don't know the process, but there's like a lot of checks and a lot of people who have to agree. And I think for the last tenders, for like some of the processing for the SCAR satellite, which we have now, I think the company could choose, like the company that delivers for us. I mean, I think of course it had to be approved, like what they bid in with, but I think they could choose the language when they made the bid.
Okay, thank you very much again. Where do you want to put this?
Gonna do some real math.
Okay, let's continue. We'll have now a hands-on session on Introduction to Applied Scientific Machine Learning by Chris Rukakis. Thank you very much.
Yep, so thank you. Yeah, so we'll see how much we can get through. I have no idea if I planned way too much or way too little, but it's not going to be correct. So let's see where we land. So what I want to go through is I want to go through deep learning, and then I want to get to a very basic example of scientific machine learning, and then kind of open up to this chat and use this as a dialogue point. So as the very first piece here, how many people are feel very good using the deep learning libraries? Raise your hand. Exactly. So this is exactly the right part to start with. So this is where we're going to start with. So I said just for the YouTube out there, right? The real audience. Hello YouTube. So I asked everyone, who here is familiar with using a deep learning library? And I think I got 2 hands in a field of, I don't know, more than 2. So, okay, so that sounds like it's not good, but okay, no, this is part of the plan. Because what we're going to do here is we're going to start all the way at the beginning and say, let's just learn deep learning, right? Now for this example, I'm going to use Lux, which in Julia there's Lux and Flux. They're pretty much exactly the same. The names are very similar. But the reason why I'm going to use Lux is, for me, it's a bit easier to show everything that's going on, because I want to kind of demystify what's going on in a deep learning library, right? There's a lot that goes on inside of them, but it's actually, you can understand more about how it works than you think. Yeah? Is the notebook found online? That is a very good question. I don't think I shared the link to it yet, so intermission. Anyone got good elevator music? All right, let's see. Anyone say on the Julia Slack that I could Slack it to very quickly? So who's someone I should be sending this to right now? Anyone on the Julia, or Simon, you'll be on the Julia Slack, aha. So I'm going to send it to Simon, and he'll find out what to do with it. Thank you, Simon, for signing up for that. All right, and he's got the link. All right. So now we're back to our regular scheduled programming. And there, the programming was a pun. All right, cool. So we're using Lux mostly because it's going to be very clear everything that's going on every step of the way. You know, down the line you might use Lux or Flux. Their syntax is very similar, but the reason why I want to do this is I want to show everything that's going on with a little whiteboard here to kind of be able to explain what we're doing. So the first things first, you install a bunch of packages. Why are we going to install packages? Well, that's how we're going to use everything. The packages that we have inside of here are essentially optimization packages, packages for representing neural networks, and packages for putting neural networks inside of ODE Solver. So first of all, why optimization packages? Well, remember that when I talked about doing this machine learning, let me open this back up. Oh no, did I close that? Pay no attention to the fact that it's still a 2023 folder. It's fine. Yeah, so at the earlier talk that I gave, right, we talked all about, was this the right, no, that was not the right deck. Yeah, so remember in this earlier talk that I gave, right, that we talked about, you know, what is machine learning, and at the end of the day, what I said is, oh, machine learning is about imposing functional forms, right? So you impose a functional form, like where you say, I assume that my relationship in the data is y equals f of x, where f of x is a quadratic function. And then what I want to do is I want to learn what x, b, and c, what these parameters are to be able to fit that function to my data, right? Now, so there's two different parts here, right? One part is how do I represent the function, and then the second part is how do I find those numbers that make this representative function go through the data that I expect it to go through, right? The first step is the machine learning library. The second step is the optimization library. And then there's also a step in here which is a library for computing gradients, and I'll show you exactly why this comes in here. But so this is our package space. Let's pull some packages in. We pull in an RNG, and now bang, we get hit right away. What is this saying, right? So this is our definition of a neural network. Now let's go write this down, right? So okay. So what is a neural network, right? Remember that in the first talk I said it's just a representation, f of x equals y, where f of x equals, well, I'm going to just write down this form right here, right? So what I'm going to do is I'm going to take a matrix W1 and multiply it to a vector. Does everyone here remember their linear algebra, matrix vector multiplications? Okay, that's getting a lot of yeses. Okay, so you multiply this vector W1 to x, and then you add a vector here, and then you do some operation. So this is going to be this thing called a tanh. And now what I'm going to do next is I'm going to do W2, another matrix, multiply it to the output there, and then plus B2. And then on that I'm going to do another tanh, and then I'm going to do another W3, and then plus B3. And this is actually the function that I've written down right there. So why does it look like that? So there's a shorthand, right? There's a shorthand where the person who's writing this deep learning library, you can write down. You could in Julia you can define. I have a matrix W1, W2, W3. You can write this down and it'll be exactly the same result as what's happening in the library. Exactly the same. So what does this shorthand actually mean, right? So what I'm really glossing over here is the sizes of the matrices. These are really the important part, right? So let's say we have x equal to x1, x2, right? So that's in math terms. This is saying that x is in R2 or it's two-dimensional, right? Right. So if our input is two-dimensional, so what did I say about neural networks? Well, if we make our neural networks be big enough, if they have enough parameters, then it can fit anything, right? Well, how do we make a neural network be sized in such a way so that way we can have more parameters while fitting the same exact functional form? this is the real question. So, and the way that you get there is let's look at some matrix multiplication. So if I do W equals W1, 1, W1, 2, W2, 1, and W2, 2, right? If I say that this matrix is a 2 by 2 matrix, right? Then if I do Wx, if I write this all out, what do I actually get from W times X? Well, you have to do your rule, right? So you do this, right? Column, right? Row. You remember your matrix multiplication rule? So let me write this all down. So you get W11 X1 plus W12 X2, right? W21 X1 plus W22 X2, and then you have another thing here, and you have another thing here, right? I'm not going to write them all down, but what you get when you multiply a 2 by 2 matrix to you multiply a 2 by 2 matrix to a 2 by 1 object, what you get is a 2 by 1 object, or oops, so there was nothing there. Yeah, so what you get is you get a 2 by 1 object, right? So then the question is, okay, if I want to add more parameters to this, what can I do? And so what you have to remember is you have to remember your matrix multiplication rules. So let's see what happens, right? So let's say I have a 2 by 3 matrix, right? So we have 2 rows, so we have W1, 1, we have W2, 1, W2, W1, 2, W2, 2, W1, 3, W2, 3. So let's say we had this 2 by 3 matrix, and we want to multiply it to this X1, X2. Does anyone remember their matrix multiplication rules? What does this look like? Yeah? Yeah. So the answer is you can't do this, right? You can't do this. It's not well defined, right? Because remember that your matrix multiplication rule is you multiply going across the row and down the column, right? So boom. So this times this plus this times this plus this times. Oh, I'm missing something. So I can't do that, right? So so if I have a 2 by 3 and a 2 by 1, I can't multiply these together. I need this 3 and this 2 to be the same, right? So the number of parameters or the number of columns is constrained. I need to choose the number of columns to be, the number of columns has to be equal to the size of this vector, right? But is there something else that I can choose here? Can anyone see? I can't choose the number of columns, but what can I choose? I can choose the number of rows, right? So what happens here? So let's say I have so let's let W be a 3 by 2 matrix, right? So now here I have a W11, I have a W21, a W31, I have a W12, I have a W22, and I have a W32, right? Very similar, it's just now has more rows than more columns. And I put this X1, X2 here. And now we do our matrix multiplication rule, right? So if you remember your matrix multiplications, I could do bam, bam. So I get W11 times X1 plus W12 times X2. So if your math teacher said, oh, you're going to use linear algebra, this is why we require this class. Well, they might have not told you, but it's because it's everything in machine learning is linear algebra. So this is one of the reasons why it's required everywhere. But if you write this all down, if you do this matrix vector multiplication, what do you get? Well, you get something interesting, right? So you take a 3 by 2 and you take a 2 by 1 object, and what do you get out? What size by what size do you get out of here? 3 by 1. You get a 3 by 1, right? And there's actually a nice rule for this, right? So if you do a multiplication here, these two have to be equal, and then what comes out is going to be this part by this part. right? So this is your linear algebra, just kind of doing a quick refresher here. But see, the key here though is if I want to use this exact functional form, right? So this is my form of my function, but if I want to put more numbers in there to have more parameters to learn, where can they go, right? Well, if my x is size 2, right? Well, then if I want to kind of grow the size of my neural network, what I can do is I can make W be a matrix that's not square. And if I make W be a matrix that's not square, I can say make there be more rows than columns. I can make there be, say, 3 rows. And now this W1 times X is now size 3. And so then this B is size 3. This tan H is tan H applied to 3 objects. And now I have a W2, right? W2, it just has to have, its number of columns has to be 3 now, right? But what comes out of there is just how many rows did I choose? How many rows do I want? I can say 16. And now the vector that comes out of here is size 16. I add 16 numbers to it. I do a tan H to it. And now I have a W3. Now I'm going to say, what does the size of W3 have to be? Now, since this is a last matrix multiplication in here, there's actually a constraint on this last one that comes out. Does anyone kind of see what that hidden constraint would have to be? So f of x equals y. We can use these matrix multiplications to grow and shrink the sizes of our vectors, but this is our last growing and shrink operation. So what needs to be true about this last matrix multiplication? Yeah, it better give you something that is outputted to the size of y, right? So this is really the key. So if we go from size 2 to size 3, right? This is when people draw a picture of a neural network, right? When people draw a picture of a neural network, this is what they're actually meaning. So, let me. So when you draw a picture like this, right, so I have that, this is my x, and it has 2 numbers, right? This is like x2, x1, right? And what we're showing then is we say, okay, there's now a hidden layer in here. x2 goes to all of these, x1 goes to all of these, and then this is my hidden layer. So this is my, h1, right? And what is h1? h1 equals this tan h w1x plus b, b1, where w1 is 3 by 2 and b1 is 3 by 1, right? And so this is what this is actually, when you see these pictures of a neural network, that's what it's meaning. And what it means here is that there are, this right here is a matrix which has W11, W21, W31, W12, W22, W32, right? It means that this is a matrix with 6 numbers in it, and this is B1, B2, B3. This is a vector with 3 numbers in it, right? So this picture, this is what it means. And so this is just one operation, right? Then the next operation is H2 equals tan H, W2, H1 plus B2, right? And now, again, so where W2 is something by, it's something by 3, B2 is that same something by 1, right? And then this gives you that kind of n as your size. So when you say like, oh, I have a really big hidden layer, right? The size of this hidden layer is just the choice for how many rows you have of numbers inside of here, right? And then the final thing is just H3 equals, H3 equals W3 H2 plus B3, where W3 is, K by N, and then B3 is K by 1, where K equals the size of Y. It's the amount of things that we wanted to output. So what you can think about it is our matrix multiplications in the middle are used to expand out the size of this thing. So that way we get a whole bunch of numbers, and then we do these operations over and over and over, and in the end we collapse it back down to the size that we wanted. And the real key theorems about a universal function approximation is that if you make this expansion big enough, if you make this expansion to be large enough, if your matrix is large enough, then this representation, the same function, can represent every possible function you can write down. That is the core behind machine learning. So now let's go back to the syntax, right? What does this syntax even mean, right? Well, what it means here is these are just the definitions of our layers. Right? So each one of these is a dense layer. Each one of these is a dense layer. Right? So this is a dense layer, where what do I have to specify in order to specify? Yeah?
I have an executive question to that notebook where your cursor is, which I think relates exactly to what we were currently discussing. Like, why would you ever go down to a single, like you have then. Why would you ever, where your cursor is right now in the notebook, why would you ever go down to a single node? Like there's a hidden layer now basically collapsing down to 1 and then getting back to 10.
Yeah, I mean, yeah, that's kind of a funky example there. I mean, that is used in things like autoencoders. So if you kind of believe that your function is supposed to live in a lower dimensional space, then you can project it down to that lower dimensional space and try to see if you can learn the lower dimensional manifold on which it is. But yeah, it probably should just be a simpler one to start. Okay. But I mean, yeah, so you can start to kind of understand how to read this, right? So what this really, all this thing means is this is a dense layer which takes in a size 128 vector and spits out a 256 vector, right? Well, how do you do that? That just means that this is a dense layer which has a matrix in here which is sized 256 by 128, and then it has a B which is sized 256 by 1, right? And then what is the function that goes here? Well, this is tan h, but you can choose any function. So you can say put an exponential function there. You could put a sine function, right? But this is a definition of just one of these layers. So what this neural network is saying right here then is it's saying when you give me an x, first apply this layer that multiplies by that matrix with 128 columns, 256 rows, and then add a number that is 256 size vector, and then apply element-wise this tan h function. What is the tan h function? Let me just kind of pull it up so that way people are familiar. Tan h is the function. It's just a hyperbolic sine function. Why is this the case? Well, it turns out that in order to be able to approximate any possible function, what you have to be able to show is that this function has to be some nonlinear function. It has to be any nonlinear function. So there's just some voodoo magic functions that people have found that tend to work well. Tan h is one of them. There's a lot more to say there, but we'll keep it at that. But okay, so what you do is you have a layer like that takes 128 things, turns it into 256. Then we have one that is 256 to 1, and then 1 to 10. And so my questions here are, for that neural network, what is the size of my x, and what is the size of my data set y? From the description of the neural network, can people see how I've designed, what kind of data have I designed this neural network for? Yep. Yep, exactly. So if you read this, it's going to turn a vector of 128 into 256 things, into one thing, into 10 things. And so your x, the size of your x, the number of features that you're learning from, is 128. And the prediction, the number of things that you're predicting from those 128 variables are 10 things, right? And so this is a neural network that does exactly that using the math that I showed on the board. And so when it shows you this is the neural network, this is what it means, right? And now when it says, oh, these are the number of parameters, right, we can actually calculate out, why is this the number of parameters? So let's look at that first layer, right? The first layer has a matrix in there which has 128 by 256 numbers, and then it has 256 numbers, right? So now let's just type this into the REPL. So we say 128 times 256 plus 256, and that gives you 33,024 parameters. So that's what that number is, right? So the number of numbers that define that first operation is 33,000 different parameters. The second one has 257 parameters. Next one has 20 parameters. And so this whole neural network is an object that has 33,301 parameters, right? And so, each one of these are just a number. And what we want to do is we want to find what is the number that I should put for all of these 33,000 numbers, such that when I put X inside of here, it gives me the correct Y. That is what we call training. Training the neural network is this problem of finding these numbers. So this dump is just showing you a lot more information, but it is exactly the same information, right? It's saying, okay, my input dimensions are, 128, and then what comes out is 256. The way that I get the initial weights, right? Well, what are the initial choices for the weights? It tells you this is the distribution that it's using, yada, yada, yada. But this is all just giving you more information about that same mathematical function. Don't be scared. It's just matrix multiplications. So what we do here now is we say Lux setup. So there is a state. Ignore the state for today. It will come into play tomorrow when we do recurrent neural networks. Today, the state is going. Oh, actually, this is not the same terminal. So let me actually just what's a nice way to do this? The state, if I print it out, you can see that the state is name tuple empty, name tuple empty, right? So today this state is empty, right? Now what state is used for is carrying along. So there are some cases where when you evaluate the neural network, you want the same inputs to give you different results. What's a case like that? Well, in a time series, you want to kind of remember your past. And so there's cases when this state is used. For now, this state, you can essentially think about it as nothing. Today, our neural network is not going to have any state, but what it will have is parameters, right? And so you can see here, these are my parameters, right? So I have parameters. So I have layer 1 has parameters. So let me check layer 1. So dot layer _1. Right? Layer 1 has a matrix of weights. This is what we call the W matrix, and it has a vector of biases. Right? So let's actually look at this. Dot weight. Let's see. Oh, is it weights? Yeah. Yeah, but it's not giving me the size that I was thinking I'd get. So ignore that. Okay, so you can see, so inside of here, though, this is showing you that, when we ask the neural network, hey, give me a setup that is, give me a setup for what the weights and initialize this neural network, right? We got to initialize it somewhere. And what it'll do is it'll just come up with random values for all of these numbers that go into here, right? It'll create these matrices, it'll put random values for all of them, and there's a specific distribution that it uses there. So it created a random neural network, or random values inside of it, and then here I'm just creating random numbers to make as my inputs, right? So, Yep.
Shouldn't the weights of the first layer have a different size?
Shouldn't the weights of the layer have a different size? That's what I'm saying. So when I'm printing it like a ps.layer 1, ps.layer 1, this is showing me that there is a matrix, right? This matrix is is a 256 by 128 matrix. For some reason, when I'm doing this dot weight here, it's not showing me that same matrix. So I'm not entirely sure why. That seems like a bug in the display, but I'm going to skip over that for now. That should be showing you this 256 by 128. But okay, so now we understand the definition of this neural network, right? What do we want to do with it? Well, so this neural network, again, this neural network I defined, we call it model, right? So what is this model? Well, again, model is F, right? And the neural network is what we want to be F, so it essentially is F. So what does it do? It's a function. The neural network is a function. It takes an X and spits out Y. Well, slightly, right? So neural network is a function F, which takes in x and the current weights of the neural network and the current state and spits out y. Right? Because we have to know what are all the values inside of all these matrices. So we can take this, so we have this vector that has all of our random numbers from our matrices, and now we do exactly that. We just evaluate model on this input x. We do this, we pass in the parameters and the current state, and it spits out the new state, which again we'll go over what the state's actually doing for recurrent neural networks tomorrow, but it spits out our prediction y. So this is just our f of x equals y. There's one extra complexity that I hid inside of here, which is that I gave it a matrix as input instead of a vector. Oh no, is that scary? Well, if you think about it, so here I had a matrix times a vector, right? So this is 128 by 4. Well, if I have 4 columns, and I do this 256 by 4, I just get 256 by 4. I just have 4 columns. And so if you pass in something that has 1 column, every single time you'll be resizing this 1 column object. If you pass in something that has n columns, you're just going to be resizing the number of rows in this n column object. So basically what you can think of is the way that neural networks are defined, it's going to do the neural network operation on this column, and it's going to do the neural network operation on this column, and this column, and this column. It's going to do all of those operations independently. So you can pass it in each column at a time, but if you go through the math, I'll leave this as a homework exercise. If you go through the math, you'll notice that each column of the input is completely independent. So it's the same thing. You can say that this is x. This is the first x. This is the second x. This is the third x. This is the fourth x. And then what comes out of this neural network is a matrix which has the first y, the second y, the third y. And so it's just doing 4 different predictions at the same time if you give it a matrix instead of a vector. But you can also just give it a vector, right? So if you then want to say, let's make this easy, right? So what is the first column here? Or no, that's the first row. Sorry. What is the first column? Well, I can also just pass the neural network this first column. And what it will spit out is, oh no, that's not good. Did I flip this around? And never do anything live. I heard that whenever you get in front of a stage, your IQ drops by 30. That's definitely happening here. But okay. But you can think about it as, you can always put in these vectors one at a time, or you can put multiple vectors in just by passing a matrix. But a neural network is just a function with parameters inside of there. Is everyone here on the same page? All right. So then the next thing is, I want to calculate derivatives of my neural network. So why do I want to calculate derivatives of my neural network? Well, the training process, training a neural network, or if you want to say it in the words of Elon Musk, making computers sentient, right, is simply a process of optimization. So what do I mean by this optimization? So what I want to do is, I want, oh no. It was too happy to be writing earlier. So I want f of x equal to y, but what I actually have, I have neural network of x given parameters equals some value y tilde, right? And I want these to be the same thing. So how do I do that? Well, what I do is I say I have a loss function. So loss of p, so the loss of my parameters is the distance between f of x and the neural network applied at x. I want this to be as small as possible, right? So this is, if you don't know this notation, this is the Euclidean distance. Or it's just, it's just y1 minus y1 tilde squared plus y2 minus y2 tilde squared plus ... right? It's just, let's take all of our outputs, let's take the difference between them, and let's square them and use the squared distance, right? So why are we doing that? Well, what this means is what we're actually doing is we're sticking in a value here, or saying it equals this, but what we want is that we want to stick in a value here and have it equal to that. So what's the difference between the two? This is a number that's just the difference between, if I put the two of them and I plotted them out, this is how far away they are, right? So this is a function that is, how far away am I from the actual predictions that I want to get, right? So what we want to do is, in order to train, training a neural network, so train a neural network is equal to find P such that loss of P is small. That's all it is. Our neural network has a bunch of numbers inside of there. Our numbers are wrong when this big thing is big. Let's find P such that this thing is small. Ta-da, that's all that training a neural network is, right? But how do we actually do that? Well, how do we do that? So how do we do that? And this is gradient, I'm going to misspell this, but descent. That's not spelled right. Other than the misspelling, this is done by gradient descent. And I think that there's an S in here. And what does this mean? Well, it means that, given a value P, a better value P hat is given by the following. So P hat equals P plus the derivative of the loss with respect to P, and there's this alpha, which is known as the learning rate. And this is just a value that you choose, right? So let's just say that this is like 0.8 or something, right? So this operation will get you a loss that's improving. Why is that the case? Well, let's just show this really quickly. What I'm saying is, let's say we have a function, right? So this function is our loss. That's actually a bad function to draw. So this function is our loss. And so what we do is we look at here, we say this is our P, and then we say, what is our derivative? Well, our derivative says, we're like this, right? And we ask our derivative, which way is going down? And it says, going down is this way. And we go, okay, there's P hat. Right? So if you just calculate the derivative to know where is up and where is down, and we'll just take a step in the direction of down. And what do? We then go from where this is, and we say, okay, where is down? Oh, down is that way. There's P hat 2. And we just keep on doing that, and if we keep on walking down, we will go to a spot that has a lower loss. And this is what gradient descent is. We just find the gradient, find the gradient of the hill, and just keep on rolling downhill until we hit the bottom of a hill. Now you might think like, oh, well, what if this happens, right? So, what if you have something over here, this is lower than that? Yeah, this algorithm will not find you the best minimum. It's not going to find you the best parameters, but we'll find you a set of parameters that makes your loss relatively good. And so then there's a lot of study in machine learning as to better schemes than this. This is the simplest one, but this is an idea of what's going on, right? So, what do you actually have to do in order to train a neural network? All you need to do is calculate derivatives of your neural network with respect to all of your neural network parameters. So this is where something called automatic differentiation comes into play. So everything at the end of the day for training a neural network is just calculating derivatives. You calculate derivatives and stick them into a function. So if you want to understand like what is Google doing when it's spending billions of dollars to build a neural network library, 99% of that time is just creating functionality to make it easy to calculate derivatives. That's all that these libraries are. They are function representations and ways to calculate derivatives. So here what I'm showing is that, we can wrap our derivatives inside of, here's one way of calculating derivatives in Julia. We can wrap these things in Tracker, and then we can say, well, let's put this into the model, throw it back, and extract the gradient. This is one way to calculate the gradient, and I think I've completely messed up a lot of things. Let me rerun a lot of these from the start. Oh no, what did I do? Right. So here is one way of calculating gradients. They're effectively the same, right? So what you do in order to calculate gradients, without all the math, I mean, you could just instead here call the function that is zygote dot. You call zygote dot gradient. Yeah. Okay, well, the output should be scalar. So that's why. So okay, let's actually take this step by step then. So remember that our function here, actually use this one for a bit. So okay, so remember that our function here takes in, our function here is a function that takes in a matrix, right, and it spits out, say, a vector, right? So, this is not something you can calculate a gradient of. A gradient is always of a function that is one-dimensional. So what do? What we'd have to do is we'd define a loss function. Like the loss function respect to p would be something like evaluate the neural network at p. And so this, let me write down this function. So I could say the loss function with respect to p is I get a y hat, or let's see, how do I get the fancy hat here? Haha. Yeah, so we got a y hat. So this is our prediction. And now what we want to say is this is y. Let's just kind of define y real is equal to, what's the size of our output here? Random of 10 by 4, if I remember correctly. Right, so let's say this is what our data actually is. We want the output to actually be equal to this, right? What I can do is I can say, well, what I want is I want to evaluate the neural network with these parameters on any given input data that I have to train on. This is x. And what it spits out is my prediction. And now I do my prediction minus my real value. And then I just do the sum squared error. Right, so this is now a function. This is now a function. This is now a function where if I do loss of p's, it should give me Did I do the sizing wrong here? Let me double check my sizing. 10 by 4. Oh, I see. So this should give me a function then where, st hat not defined. There we go. This now gives me a function where I give it the neural network weights, and it gives me out, this is how far the prediction from the neural network is from this random vector I just constructed, right? So this is a function. This is exactly this loss function, right? It's a measure of how good my neural network is at doing something, right? And normally you want to kind of say like, oh, this is my measurement of how well my neural network is at predicting what you'll want to write next inside of the search bar, or what you would write next in your essay, et cetera, right? So this loss function is how you construct your neural network to do something, right? Here what I'm saying is something rather trivial. I'm just saying make the neural network spit out an output and see how far it is from this random vector that I constructed right here. That's not very exciting. What this will do, though, is it'll train neural networks that take in values x and spit out these numbers right here, right? So it'll train a neural network to do that, but I mean, if you have real data, this is where you'd put your real data right there, right? You want to learn something that takes in real values and spits out that thing, right? So there you go. I have a loss function. When I put in a value of neural network parameters, it spits out a number, right? This number is 12.849, which is just a number that says, you wanted this, you were over here, the distance between where you wanted to be from where you are is 12.8949, et cetera, right? So what we want to do is we want to make that number be as small as possible. So we just calculate, say, let's see. So we now just say, if I want to do that process, I would do exactly as I described there. And I would just ask it for the gradient. And let me double check here. I should make this loss function be a value of x, p's, and st. Sorry, x, p's, and xt and st. And so now I'm going to ask it, give me the gradient here. And it's going to give me the gradient of the output, the derivative of the output with respect to all of the neural network weights. Where was that? All the neural network weights. Actually, it gives me more than that. It gives me the derivative of the output with respect to the input x, and then it gives me the derivative of the output with respect to the neural network weights, and it gives me the derivative of the output with respect to this input state. So it just calculates all the derivatives, and then you can use that to be able to write down this kind of functionality. There's other ways to calculate the derivatives as well, but essentially, what is the part that you should think of as a black box? What is the thing that if you're using a neural network library, why are you using it? It's because this process of how do you get these derivatives, this is what I would teach a 3 month long in a class, right? That process of actually doing that calculation, that's the hard part. But if you just assume that you can get gradients, everything else is easy to understand. So now let's actually look at this, right? So let's have a function here. Let's have a function here which generates data. So here's my test case. Here's my test case. I just say, we have some values x and y. Let me actually do using plots and then plot x, y. Hopefully this is, how do I do this here? Okay, well, I did actually have it down here. So here we have this kind of data set generation process, and what it's doing now is it's just generating data from a quadratic function. So here's the true function that I use to generate the data, and I just put a bunch of noise around it, right? So here is my data set. And again, how can you fit this? What would you do? What would you call machine learning? Well, the first thing that you probably want to do is find a better function, right? What's a better function to fit that? Well, if you look at this and you're a scientist, you should say, that looks quite quadratic, and you should fit a quadratic function through it, right? But as an example, right, a neural network is able to represent any possible function, so let's have it represent that quadratic function, right? So, okay, what we do is we then just, we define a neural network. You can see here that, if we want to learn a quadratic function, quadratic functions are not that hard, right? So let's use a very small, relatively small neural network. It takes in one value, right? So we want to learn from x, we want to find out y. So it takes in one value, it goes up to 16, it does a few computations of the same thing, right? What is the GALU layer? So the GALU layer is, it's just a ReLU that has a machine learning. Randomly typing into Google is kind of scary to do if you're also live. The internet has weird things. But here's the GALU function, right? Why is this one chosen? Again, there's a lot of study as to, these specific loss functions, et cetera, do well or worse. But, GALU, ReLU, there's just different functions that people tend to put here. So this is, so what we do is we do a ReLU at first, and then we do 3 layers, or 16 to 16 GALU, right? And so then we bring this back down to 1. So this is just a function that takes in one object and spits out one object, right? And we want it to learn to be a quadratic function. So here's our model. Here's our loss function. What do? Well, we take in our, what we do is we take in our data set, we apply the model to our data set at our current parameters to get a prediction. We take the difference between our prediction and our, we take the difference between our prediction and our data points that we wanted to hit. We take the take the mean squared error of that, and there's our loss function. Right? So what we do is we just do that now. We just do that. So we just say, okay, this is all I'm doing. I'm defining a main loop where I just basically say, for each epoch in epochs, do the training thing of applying the gradient. So it'll take the current parameters, it will then calculate what the gradient is, and then it'll move the parameters by the amount of the gradient, and it's just going to do this over and over and over and over in a loop. And now let's actually run this. And now it's a very tiny neural network, so it's not going to cost the billions that Google's using to train, right? This is just a few numbers. But you can see that here, what it does is it says, okay, I have some parameters, and at my first parameters, it has a loss of 8.47, This is how far they are, right? Then it found new parameters that are closer, new parameters that are closer and closer and closer and closer. Sometimes, oh no, it goes back up. Why does that happen? Well, sometimes if you say, well, let's walk in the direction of downhill, it's going to jump too far and actually has gone uphill again. Oh no. So it has kind of algorithms that know, actually make your jumps smaller and smaller as you do this process. So again, there's more advanced things going on in some parts of this algorithm, but this is really what it's doing. It just keeps on walking, and it says, you started with parameters that were not very good, and now we got parameters that were reasonably good. Right? So let's actually plot it. So what this does now is, okay, once we've trained this neural network, right? So when we train a neural network, what did we learn? What comes out of this training process? Let's see who's following. When I finish this training process, what do I have? You have the weights, right? You have the numbers. You have the numbers that go into these matrices. You have the numbers that go right there, right? So what this loss value means is that on the data that you trained on, with the data that you trained on, if I stick my inputs x and use these values of the weights, that loss value is how close it got in distance, right? So now what do I want to do to be able to evaluate that my machine learning model has actually learned something that is predictive? Well, let me take all the x's, put in the weights, I get a bunch of y's, right? And now let me just plot those y's right next to my data set and see how good it is at predicting. That's all that this is saying here, right? It's just saying evaluate this neural network and then evaluate the polynomial, And what you see here is then this is what this prediction is. So the neural network is the predictions are in green. The actual data that it learned from are the orange. And what it's learned is it's learned to be a function that's a lot like our quadratic function. So yay, we just went through hundreds of parameters and a deep learning library and all that to be able to learn a quadratic function, which you might have done in your undergraduate stats course. But the thing is, this is a completely general process for learning any possible function, right? So okay, the next part is on GPUs. We could skip GPUs and debugging. I mean, so GPUs and debugging, so what is the biggest thing that comes into play when trying to debug neural networks? Well, the biggest thing that you have to worry about is your sizes have to match up, right? If you do, if you do, you know, the 16, 1 to 16, 16 to 3, 1 to 1, you know, what's going on here? Anyone see what the bug is in here? Exactly. So, you know, again, remember, you know, you have to have the size of these matrices all line up. So the first matrix is going to take something that is of size 1, bring it up to size 16. Then it's going to bring it from size 16 to size 3. And then the next one is a layer that takes in something size 1 and spits out a size 1, but its input is size 3. So you're going to get an error if you actually try to run this. And so the deep learning libraries, they have all these tools for being able to do this debugging, for telling you, you know, what, so, you know, if you just run it, it's just going to say dimension mismatch, you know, et cetera, et cetera. What is this actually saying? Well, this is actually saying is, you know, this W3 tried to do a matrix multiplication. So this W3 tried to do a matrix multiplication against a vector. That vector was size 3 by 12, but it was a 1 by 1 matrix, so therefore the sizes don't line up, right? As I described, the sizes have to be same in the middle. So, you know, so sometimes reading this kind of bug can be kind of difficult, but it's, at its core, though, it's just really easy. You know, it's just that, okay, this number should not have been a 1, it should have been a 3, right? And so there's also types of tools inside of these neural network libraries to be able to tell you, you know, in this layer everything matches up, in this layer everything matches up, and oh, this failed because you had the wrong size here, right? So, you know, if you go through the tutorials of these libraries, they have all sorts of pieces to be able to tell you, like, hey, your mathematics does not make sense here, or it does make sense, here's where it doesn't make sense. And, you know, these are all library features, but again, if you understand the mathematical definition of what's going on here, you can kind of look at it and say, oh, you know, it can't make sense to do this operation because the matrices are the wrong size, right? And the actual error message that it gives you is an error message about matrix multiplication. Machine learning is just matrix multiplication at the end of the day. Okay. So now I want to get to this last part here, which is now finally the scientific machine learning. So this was just deep learning, right? So, you know, you approximate functions with machine learning. And now the last part here is let's take our function approximators and stick them inside of an ODE. This is probably a bit of a jump because we didn't go over the ODE solvers and all that, but I just kind of want to, you know, make sure that we have a nice fun ending because I'm just over time. But what we could do is we could say, okay, I define a neural network, right? What is a neural network? It's a function. That's all it is. And so I want to define a ODE where this ODE takes in a value u and spits out the derivative. How do I define this? How do I define this derivative function? I just tell it, evaluate the neural network, and I'll use the neural network's value as the derivative, right? So the model that I just defined here, is just u prime equals neural network of u. Right, let's read this again. So without going through the ODE solver library, you know, what I'm doing is it says, okay, tell me how to calculate the derivative of the ODE given the current state u. And what I do is I just take that value, I stick it in the neural network, and I say, whatever comes out is the derivative. So this is exactly this model right here. U prime equals the neural network. And yada, 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 details. But you can see that when you evaluate this on values, your neural network is then spitting out, hey, here's what your current derivative is. And while, you know, an ODE gives you a time series, what we do is we can solve this ODE defined by the neural network, and it gives you a time series. And then you say, okay, well, I want to train this neural network. How do I train this neural network? Well, I take derivatives of the time series outputs with respect to the neural network parameters. I mean, it's a bit more, you know, there's a bit more that's going on here, but essentially all that we're doing is we're solving an ODE to get a line, and we're just asking the question, how does this line change as I change my neural network parameters? Does it go up? Does it go down? And if I want this to match a time series that I have, well, how do I change my neural network values, or my neural network parameters, such that it goes through the time series? And, well, how do you do that? Well, you define a loss function where you say, create the ODE, solve the ODE to get the time series, and then check its distance from whatever you want it to hit. So here I'm saying, let's train this neural ODE to give you a time series that is 0. It's kind of a toy case, but let's learn let's learn neural network weights that will give you, so that way you learn a time series that's spitting out 0. And that's all you have to do. You just put, if you could calculate gradients, now you put it in the same loss function that we had before, run the training process, and boom, you find neural network weights that makes it into any function that you wanted, right? So that's with ODEs. I'm over time here a little bit, so let me then say, you can do this, for example, with nonlinear functions, right? So what is a nonlinear function? So let's say now we have f of x equal to f of x equal to 0. Find x, right? So what is an example problem like this? This is like f of x is equal to x1 plus x2, x2 squared minus x, right? Or x1, right? So it's this kind of function where you say find x1 and x2 such that this is equal to 0 and this is equal to 0, right? So there's a lot of mathematical models that people write as these kind of algebraic expressions, right? And what we can do here is we can say, well, here's an f of x. Let's learn that. Yep. Oh, I do? Oh, wow. I thought it was supposed to be done in 3. Okay. Oh, that completely changes things. Okay. Okay, yeah, I looked at the, I'm very confused what to do with that time then, but more time is always good. So let's learn this function, right? So the problem here of learning a nonlinear algebraic function is really just that, what we want to do is we want to find, find x such that neural network of x equals 0, but then we want to find p such that the output x is what we wanted. Right, because so let's look at this function here for a second, right? So if we were to do this, we'd have to have that the square root of x1 equals x2, and then we would have that, and then we'd also have that, so we'd have x1 plus square. Well, I guess yeah. You could probably write it as x2 squared plus x1 is equal, or x2 squared plus x2 equals 0. This is a quadratic function. What's the solution? Well, it turns out that actually one of the solutions is 0, 0. Oh, that's an easy one to write down, right? So this process defines a function such that given a neural network, it will spit out a value that satisfies or given a starting point, it will spit out a value that satisfies a starting point, right? Well, what we can do instead is we can say, I want to learn this function that learns what the equilibrium is, right? One equilibrium is 0, 0, but there's other equilibrium. So if I have values at the equilibrium, can I learn a function that spits out, that tells me how to calculate equilibriums, right? And so what you do is, well, are there libraries that solve this kind of problem? Yeah, there's many libraries that solve this kind of problem. So what we do is we give it a function, this f of u, where it's where the solution to this nonlinear problem is the solution to finding the zeros of this function, right? So this is defined as a nonlinear problem, where now instead of actually writing down the function I want to model, I just say, I'm going to use the neural network as the model, and I want to learn what the model is. And so then I put this in the nonlinear solver, and I think that I might have messed that up, so let me go to my notes here. My original notes before I messed everything up. Note to self, don't keep on typing live into a REPL and then forget what you put there. And so then, I can solve this problem, and what it'll do is it'll find values of u that satisfy neural network of u equals 0, right? It's just, it'll run it through this same solver, because the solver doesn't care what function you give it, right? You define a function, and it will solve, neural network of f of u equals 0. F is just a neural network in this at this point. So now I can just give it different values of f, and I can use this neural network as my model. And so I can do now exactly the same thing I did before. I just say, okay, I want to learn what my model should be. Well, I stick the model inside of a loss function. What do I want my model to do? Well, I want my model to give out values that are 0. I don't know. This is a test function. I do this, and then I stick my loss. I have a loss value, right? I can take gradients of it, so I can do gradient descent. And now for any kind of output that I wanted to do, I can learn what this function would have been that would make the model correct to what I wanted, right? And if you go back to that first talk that I gave, this is how you then, all the things about, doing this COVID modeling, yada, 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 are all exactly the same thing, right? So let me go all the way back to the start and say, what did we do? So what is a neural network? It's a function. It's a function that just has a bunch of numbers inside of there. And it's designed in such a way where if you make the numbers, if you have more numbers, if you have enough of the numbers, then it can match any possible function. And then what we do is we could just come up with an algorithm that tells us, that is, oh, this tells me if my numbers are good, if my parameters are good, and I will run this process. I will run, this is actually more difficult to get. And I will run this process of just continually walking down the hill using a gradient in order to find out what good numbers are. And once I have good numbers, what I have is I have a good representation of f of x equals y. And I can do that in any place where I would have written down a function. So any function you would have written computationally, you can now say, well, instead of writing down this function, if I have input data and output data, I can have a neural network just take in inputs and learn how to give you out the same outputs. And now everything from ChatGPT to things that are doing facial recognition are all doing exactly this, with slightly different definitions in the neural network, slightly different definitions of optimization, but this exact same process is what's going on. So hopefully that kind of illuminates what machine learning is doing and all the different cases with it. There you go. That's how you do machine learning in whatever time that is. Thank you. Any questions? Yes.
It's just a question to the notebook, because I've been looking like a little bit on some of the tutorials and things like that. Mm-hmm. There's flux, and then you're using lux for this notebook. Mm-hmm. What are the differences, and which one should I use?
Yeah. So the key here is, so what is the differences between lux and flux? Very good question, because they're actually more similar than not, right? So if you look at the way that they actually define all of these mathematical operations are all exactly the same. In fact, they're using the same exact libraries underneath the hood for the definition of all of their mathematical pieces. So that library under the hood is nnlib.jl, and so in a sense, they're exactly the same library. So they're both using this nnlib.jl, which is just a way of all of these different layer definitions for all the different functions that go into a neural network, right? So what's actually different here, right? And the reason why I was using this is because, so in Flux, let me actually just show this. In Lux, what you have is when I create this neural network, where's the easiest way to show this? So here I create a neural network, right? And this neural network is just a function. And then I say, instantiate this neural network, and it gives me parameters and it gives me states, right? And now I have neural network parameters and states, and now whenever I want to evaluate the model, I just pass it a set of parameters and I pass it a set of states, right? And that does an evaluation. And so this makes it very easy to kind of say, oh, what are the parameters? Let me look into them. And if I want to make them be a vector, you can do all sorts of things with them because you have direct access to your parameters, right? Now let's look over at Flux, just to kind of see. Again, the mathematical operations are defined exactly the same. So what's different is you can see that when this person in the tutorial, when they evaluate their model here, right? When they evaluate their model, they don't actually pass in their parameters. The reason is because the neural network model itself actually holds the parameters internally, and it knows magically how to update them, right? The more magic that you have, the more difficult it can be to do certain things. Like, for example, if you want to take your vector parameters and, say, evaluate a Fortran function on it or something, right? That's rather hard to do with Flux, whereas with Lux, you just ask for the array parameters, do it, and turn it back into what it wants, right? So I find Lux to be a bit simpler to work with the scientific machine learning tools, though it does all work with Flux as well. But there's differences between them. But it really just comes down to this question of are you more happy to have your parameters be explicit? Like, do you want to hold on to your parameters and pass them, or do you want to say the parameters are inside the model and let the system handle the parameters, right? It's a bit less flexible, but a bit higher level. But I think in terms of teaching, it's nice to kind of show like here's what this is equal to, and all that as well. But yeah, that's essentially the only difference. At a high level, just have you wrap the parameters into the model or have you not? Yep.
Do you know what is the state of using 16-bit floats with neural networks?
Yeah, I mean, using 16-bit floats with neural networks is fine. I mean, so the key, though, is that I think most x86 chips, right, they don't actually have a native float 16 operator. A lot of GPUs do, right? So if you do this with GPUs, then it'll make use of, I mean, so what exactly is going on under the hood in these libraries? Let's actually just show it, right? Right? So Julia has this advantage that people write Julia in Julia. So let's actually just show this, right? There's nothing scary about these libraries. Let's actually look at Dense. Hopefully it hasn't changed since the last time I've done this. Let's see. Well, let me actually just find it. I think I know where to find it in here. You go into the code, you go into layers, you go into basic, and you see, okay, chain. What is this chain object that we've been using, right? We chain over things together. Well, all it does is it's just evaluating each. It's just evaluating each one after the other, right? Okay, good. That's just the function definition. Yep. So the chain object, right, is just apply chain, which is just evaluate one object, call the first layer, then call the second layer on that, and then call the third layer. It's just successively calling functions. It's a pipe in a different form, right? So then the next thing is how is dense defined, right? So right here is the definition of dense inside the library. Well, here's the doc string. So here you can see this is flux. Why is it flux? Well, because it has its weight, its bias, and its activation function defined inside of the layer, right? Instead of having the parameters outside. And when you call dense on a input, what does it do? Well, first it checks that the sizes of everything is okay. It checks that the sizes of everything are okay. Then actually replaces things with the fast thing. So, right there, you can see it's actually doing fast mouth operations, if you know what those are. There's good things and bad things to that. That's standard in a machine learning library. But then you can see right here, it does the weight matrix multiplied by the input, and then dot plus the bias, right? So is float 16 supported in here? Well, is float 16 supported by Julia for matrix multiplication? Is it supported by Julia for matrix vector addition, or vector addition? And is it supported inside of the fast tanh function? If those three things are true, then it's true. And so, for example, so it works well on GPUs because the GPU libraries define the matrix multiplication and all that, which I think, in your talk you'll talk about, right? You'll use these exact same operations for doing that for your work, right? And what I'm showing here is then there's nothing different about the machine learning library, right? It's literally just doing a matrix vector multiplication and then doing a dot plus and a dot and so if those operations work in Julia, then they work in the machine learning library.
And I'm wondering if I want to pass the weights of the state to 32, I just cast it to 32. There is no. That's all would be necessary to use.
Yep. Yeah. You just cast that these these parameter values should be float 32 or float 16. You just cast them to the types that you want.
Thanks.
Yeah, it's another good. It's more. So, do you have any experience with Earth observation data and weather models? And have you done anything with that at Julia Hub? Do you know of any projects?
I am not an Earth observation guy. I have to be very sad when I say that in this group. I am. All right, I'm out of here. Thanks.
No. So, when will you do something with Earth observations and weather?
Yeah, I mean, so we have done some things with the numerical weather prediction. So we've actually done a lot with the CLIMA group, right? So MIT has a collaboration with Caltech on building climate models, right? And there's this pure Julia-based climate model. And so one of the things that starts to happen is when you say, okay, the whole stack is Julia all the way down, we look at that and go, hey, we can actually calculate gradients of their climate model, right? If we could calculate gradients of their climate model, then we could stick neural networks in there. So that is something that we've been working with. We have some papers on how can you find better parameterizations of ocean models and things like that, and also trying to find out some relationships between, if you have, say, satellite data that is trying to tell you a relationship that is telling you, the phytoplankton in the water is the one that I mentioned because that's the one that I've actually been talking with some folks at MIT about, right? That's about as close as I've gotten to it. But again, there are people that are building these climate models. Anything that's a pure Julia code, you can stick neural networks in there and you can do this operation. So I'll say I don't need to be the one to do that. You are now empowered to start doing that part yourself. But I'd be happy to chat with you online to get you any help you need to get started there.
So we have an online question here for you, Chris.
Yep.
So how does SciML support the sparse identification process that was described earlier, between parentheses, making models interpretable? If not in SciML, what's the recommended place to learn more about this?
Yeah. So there's a lot of work going on in this. So it's a bit in flux right now. I'll say I'm sorry because things are going on. But what is going on right now? What do we have and where are we going towards? So the first thing is, so we have this data-driven DiffyQ, right? So we have data-driven DiffyQ, which is a library. For example, so here's data-driven DiffyQ applied to finding the Lorentz equation. So what you do is you define a data-driven problem, which is basically you tell it, what is my x values, what are my y values, or you can give it a time series. So the ODE solution is just a representation of a time series. And then what you have to say for these algorithms is you have to say, this is the basis on which I want to learn. So I allow my function to be any polynomial of x, y, and z up to a fifth order and some other operation, right? So you can go into the library and you can see how you can say, oh, give me all the trigonometric functions, give me all the hyperbolic tangent functions or hyperbolic sine functions and such, right? So you tell it, this is the space of functions I want to live in. And then you define what algorithm you want to use to be able to do the sparsification, and it solves it, right? And then it says this is the sparse representation of the equation I was trying to learn, right? So data-driven DiffyQ is a library for doing this, and it's a library that has a lot of these sparse matrix types of operations and convex optimization methods, right? There's a very different way of doing this kind of same operation, and there's actually a very nice package for this in Julia. Actually, this is actually a case where the actual Python packages that people use are actually calling Julia packages, right? Like at this point, people in Python are just using the Julia stuff here. And this is the symbolic regression library, right? So symbolic regression.jl works rather differently. What it's doing is it's doing a evolutionary algorithm process or a genetic algorithm process for being able to evolve a set of equations. So it takes in a different representation of what space is it going to walk over, but essentially does a similar thing, right? So it defines a loss function, and it finds a sparse functional representation of that loss function. We kind of know that the community is switching back and forth between these packages and methods all the time. So what we're trying to build next is something called modeldiscovery.jl, which will have an interface that interfaces to all the different ways of doing symbolic regression. And we want to create a paper that then is benchmarking all these different ways to be able to tell people, oh, this method is good in this case, and this method is good in this case. At this point, we have 2 different libraries with 2 different sets of methods, and which one will work well for your problem, we'll try both. But we hope in the future, this is active research on these different methods, and active research and also just developing them, also active research on finding out empirically in what scenarios each one does better or worse. What we are finding, at least, is that the different methods work. There's trade-offs between the 2 of them, right? There's a lot of trade-offs in terms of if your data set has more noise or less noise, if your data set has larger values, smaller values, etc., then different methods might do better or worse. And so it's not like I can recommend one or the other. Right now we don't. But right now we don't have a good enough representation of the landscape. So yeah, this is ongoing work. But hopefully with these 2 packages you can at least get started, and hopefully in the near future it'll begin to look better and better and nicer and nicer.
Chris.
Yeah, thank you.
So since we have some time left until coffee break, we thought that Milan could talk about the speedy weather. So it was supposed to happen on the expert hour, but if we have time, I think that we should take the advantage. Thank you, Milan.
Wonderful. Hello again. I already presented on Tuesday a little bit on performance and parallel computing. Now I'm presenting a little bit more of what I've been working on over the last year and a half or so, because one of basically my pet project is called Speedy Weather, which is an atmospheric general circulation model, and it's basically supposed to be a playground where a lot of the ideas that Chris has been talking about, we kind of want to stick them in. So we will definitely find some of these ideas of representing certain terms with neural networks. These are all things that are on my to-do list, and not just with an, old school Fortran model, but that's why I wanted to create first a platform where you could actually do this in a hopefully easy way. And so this is why I've been building Speedy Weather. And Speedy Weather, therefore, is a little bit different to, let's say, the other models that we've been heard about. For example, Mohit, which has been developed for, 1985? So that was definitely before the times of Fortran 90, so it's been a while. This is more a project of me plus a few others, and it's more the timescale of 1 year. But we hope that in the future this will kick off more and more. Because, and this is where I got really frustrated about climate modeling in the past, is that a lot of climate models, especially when they're written in Fortran 90, or even 77, there's some models, I've seen some models written in 77, they are incredibly hard to use, and a lot of the research projects that I've seen that people want to do basically become an entire PhD project, meaning that people have to work on it for 3 years. If instead we could basically come up with an idea and implement it, let's say we come up with an idea on a Monday, implement it on the Tuesday, then we could basically have the results on the Wednesday or Thursday, write a paper on it on the Friday. This is kind of what I would love to be able to do with a climate model, so it should be really that easy. And so as an analogy, and I saw this I think on Twitter a couple of years ago, where someone just built a hurricane from Lego, and kind of this is what I would like a climate model to be. So really something where you can almost like play as if you play with Lego with it, because if you ask a 5-year-old here, like, what would a simulation of a hurricane look like without precipitation? That kid would probably just take away the blue stones, and this is exactly what I want a climate model to be. So like if you say, I simulate a climate model, I simulate a hurricane, and I can just like tweak the precipitation, for example, in it in a super modular way so that it's intuitive and you press play and it still does it. One of the problems that I realized while building Speedy Weather is that a lot of the current models that we have are written in a way as like what we often call like a monolithic interface. So they have something like a parameter list. So you compile your model and then you have some kind of parameter list, which is often called like a name list or so, where basically all of the parameters you could change go in there, and it basically allows you to do what the developer wants you to do. But if you want to make any more substantial changes, and this is why I've basically drawn this pyramid. So let's say you have your name list and you cannot change the precipitation in the model as you would like to, but the precipitation is actually somehow defined in this green block, which is like further down. Then it becomes a PhD project, because the PhD student then suddenly has to say like, okay, well, I need to somehow branch off from this green block, but then the PhD student need to understand how all of the interaction with the yellow and the blue component, which might be somewhere hidden inside the model, then somehow, how does the information from the name list then propagate down, and so on and so forth, and everything becomes really complicated. And so we thought like, well, why do we actually do it this way? Why can we not just somehow do it differently? And the solution that we found, and is very much inspired by Oceananigans, Chris just mentioned Klima. Oceananigans is one of the projects that came out of it, and so by talking to the Klima people, the Oceananigans people, I've basically also adapted a style, like a model constructor interface that I call it, where you basically flip this pyramid on its head. So instead of saying, I have a model and I can run it, you start by building it as if you build it from Lego pieces. And so the model components are basically now sitting at the top. You can basically create these components as you like. And then you pass them all on to a model, and then you say like, here, these are my pieces, I put them into a model, you can initialize the model, and then you can run the model. And so in that sense, we really try to build things up more like from ground up, instead of saying like you have like a single interface where you can go at the top. And so Julia was really amazing for creating these kind of ideas, to play around with kind of ideas of how can you create a climate model, or an atmospheric model in this case, where as few things as possible are hard-coded in. There is still a few things that are hard-coded in, and we deliberately make this choice because sometimes it just gets too complicated if you make everything flexible. But the things that we really care about, for example, that you can play around with different physics inside the model, those ones we didn't want to hard-code. We want to be able to pay people to just exchange them, right? So the green box could be, ideally, be replaced, for example, by a neural network that could then learn something. And so just to talk a little bit more about what is actually happening inside Speedy Weather. So Speedy Weather is a spectral model, meaning that you have two ways of representing every field, either in grid point space, what you can see on the right, or in spectral space with the spherical harmonics, what you see on the left. So that is basically, if you haven't heard of spherical harmonics yet, it's basically a Fourier transform on the sphere, and you basically have two wave numbers. Because it's a sphere, it doesn't actually end up being like a square matrix, it actually ends up being this triangle. And so if you choose more of these spectral modes, then you also get a higher resolution in grid point space, but there are some freedoms. And so the way how these spectral models work is that basically you start in spectral space, you transform into grid point space. Some of the computations are done in spectral space, some are done in grid point space, and then you transform back, and then you have the next time step. And that way you kind of jump back and forth all the time. But you choose whichever operation you have to do on a given time step. You choose whether you do it in spectral or in grid point space, depending on which one is easier. And so often that basically means you get rid of all of the stencil operations because they're hidden in the transform. So talking about flexibility, speedy weather, and talking about globes and spheres and maybe also of Earth observations, I don't know exactly what kind of grids you all use, but speedy weather has a grid flexible spectral transform. So meaning these are, for example, 6 of the different grids that we can use. You can technically just define your own and just pass that on. It works. This is exactly how we also defined these. So some of them are quite, probably the most of the data that you use comes in the one that you see in the bottom left. That's like a regular latitude-longitude grid. But you can also use these reduced grids that basically have then fewer points around the poles. And the grids here that we see on the right, these are heel-pix grids. They are all equal area, so every grid cell has actually exactly the same area, but there might be a bit then deformed so that you can actually cover the entire sphere. And just to show you some examples, speedy weather is actually several models in one. At the moment, we have 2 2D models and 2 3D models implemented, but each of them can obviously have its own individual terms and you can play around with it. So this is a simulation, I'll just press play here, where this is just the 2D barotropic vorticity model that sits on the sphere. So you basically just have a 2D flow on the sphere where you stochastically start stirring the flow, and therefore these eddies develop. And we basically just implemented this S term. You can just do it in a notebook. So I'm not going to show exactly how this works, but there's a few rules you have to follow, and then you can basically in the notebook define like, I want to define my stochastic stirring. This is what's supposed to do, and then you just pass that on to the model. That's one example. Another example is another 2D model that we have is the 2D shallow water model, which doesn't have just one equation, but basically 3. So there's 3 variables now, but still 2D. And that one is just where we start with some random waves, and if you press play, these waves start propagating around and basically then start interacting with the orography. And so that's why it kind of looks like water in a pool, because it's essentially, from a physical point of view, it's a very, very similar problem where you just have a 2D atmosphere that's some kind of thickness, and then the waves propagate around. And then to the 3D models, the equations that we solve there are called the primitive equations. So at the moment here, these are just examples. There's also videos in a second, but some examples of like a 3D model then includes humidity, temperature, and also humidity is, for example, removed, which is then precipitation, right? So whenever the humidity gets above a certain threshold, either through condensation or through convection, then basically there's a tendency of reducing the humidity, which is then basically translated into precipitation because it leaves the column and it can evaporate again in the bottom layer by evaporation from the ocean. So that's humidity in there, and then the wind speed is just another perspective of the vorticity that we've seen before. And so, for example, to show if you initialize the model with temperature, this is currently what it looks like. So you can see some leftovers here from the mountains. So you see that the temperature on top of the mountains is a bit lower. These are some setups that I've been playing around with to understand how the model works, because it's still in development. There's obviously always things that need to be changed. This is another video of precipitation that I've just recently, and you can see some things work and some things don't, but that's also okay because it doesn't have to be perfect, because I don't want to optimize it by hand, as basically most of the models in the world have been tuned. But we want to do this, we want to automate this and basically just put a neural network in and then basically say like, well, learn whatever's missing here. Because you can see that basically somehow the Pacific, it doesn't really rain in the Pacific, but it somehow rains in the Sahara, which is obviously not what you would expect. But that's also okay because it rains, and the rest is basically something that we want to correct in a more automatic manner. And so just to give you a little, I need to make this bigger again. Oh no, I have also this what was it again? View Zen mode. Yes. Here we go. Oh, but I might want to just. How do I? Clear output of all cells. Yes, here we go. So the way how you use speedy weather is, of course, using speedy weather. Let me make this a bit bigger. And the very first thing that you always define in speedy weather is the spectral grid object, which is basically the reason because the defining how you discretize your sphere determines a lot about what is the size of all the different arrays that you need to allocate. And so exactly the logic behind it is basically the first thing that you do if you want to do a simulation is like you want to define where you want to simulate something. In our case, this is always the sphere because of the spherical harmonics. And so here in this case, we define a grid on the sphere in terms of its spectral space as well as the grid point space because of the spectrum model. And so, for example, the 63 now means that this like triangle of spherical harmonics has 63 columns as well as 63 rows. And then we have like one of these grids that sits on top that has around about here a resolution of 200 kilometers, and we use just one vertical level to, for example, have it then in 2D. But there's not more that you have to define. And then you start, and this is exactly where we flip the pyramid on its head, then you start defining all the components that you want to be somehow different to the default. And so just to show, for example, we want the initial conditions to be some random vorticity, but we want to create the planet that we want to simulate on is that we create just like a planet that's like Earth, but with a rotation being equal to 0. And so you see that you could technically, and this is where the whole thing becomes really flexible. We could just define your own new planet. You could define Mars, and then say whatever Mars is supposed to have in terms of like rotation, gravity, blah, 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 all of these kind of things. And then you could just basically say like, my planet is equal to Mars, and then it would basically do the whole simulation on Mars. And then this is the magic step is where you basically throw in all of these components that you want to have that are not supposed to be the default. You just throw them into, in this case, it's the barotropic model, because it's the 2D model that we've just done, easy one to understand. And then you see that basically the planet will then be used, the initial conditions as we defined will be used, and then you've created your model, and these are now all the different components, all the different colorful blocks that I've shown earlier. And there will be things like we could have defined a forcing, a drag, all of these different terms. There will be things like an output writer, some feedback, all of this kind of stuff. But at the moment, all the components, so really constructing a model really just means that you kind of just like pull all the pieces together, you just gather them. And then the next thing that you have to do, and this is where I love it with Julia, because of the just-in-time compilation, you basically flip completely around of how you would do it in Fortran, where in Fortran you would first need to compile the whole thing, and then you can basically pass on your parameters. And here, the step of the actual compilation isn't actually done yet, but the initialize already allows things to communicate. So like basically the initialize function calls the initialize function for all of these different components, which for example allows if the forcing, let's say, depends on the gravity, but the gravity is actually, guess what, is a parameter of the planet that you're simulating, it could basically communicate that across. And so this is where then the simulation, the model is initialized and it gives you a simulation object. So the simulation object really contains everything that is in this model, all of its parameter, everything that you have to pre-compute it, blah, 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 including all the variables. Some of them, we call them prognostic variables because these are the ones that really define the model state and define how the model goes from one state to the next. And then the diagnostic variables are the ones that are kind of like diagnosed from the prognostic variables. So they're kind of all the intermediate auxiliary variables that you need to pre-compute in order to know how to get to the next step. And then really the last thing that you do is you just run your simulation, and bing, that just ran here in my notebook. At the moment we still have this funky Unicode plot that just gives you a little idea of what actually has been happening. You can obviously just turn the output on and then actually look at it in terms of netcdf files. But I found it super useful as like an interactive tool to understand what's happening. Oh yeah, does it look physical? Okay, good enough for now. And this is where like we use these Unicode plots to understand what's happening. So if you wanted to run it again, I would just press enter again and I would see like, oh, I've simulated another 10 days at a given speed here of about, well, 2,400 days per day, because, well, guess what, the simulation isn't super high. So let's do something a bit more exciting. Let's do, for example, and this is where we now define our spectral grid, not just with one level, but actually with 8 levels. So now we basically discretize the entire sphere into 8 different layers. So we're now in 3D world. But I reduced the horizontal resolution a little bit just to be able to run this on my laptop here while I'm basically presenting. And we would construct the model as before, but because now we're doing this primitive wet model, so that's a primitive equation model that also includes humidity. So you could also do it without humidity. You could basically think of a dry atmosphere. And now suddenly we have a model that has way more components. So you see here there's things like, there's an ocean model, there's like orography, there's a land sea mass, there's things like condensation, there's some thermodynamics in it, evaporation. And you could basically, in the same way as before, you could just basically define them as you want and just throw them in. And this is how you define your new model. And then you do the same thing as before. You initialize that simulation. And the cool thing is, and this is what I really love about doing these kind of simulations in Julia, is that at any point in time you can interact with all of your objects, meaning that I could also just, like, before I even run the model or after I run the model or in between, I can just investigate what's happening. And so here, for example, I'm just plotting the land sea mass that's currently part of the model, but I could also plot anything else that's inside the model, and you get a rough idea of, this is roughly the resolution that we're going to simulate in a second. So you see the continents look a bit pixelated, but that's fine for now because it's just in my laptop here and it should be quick. But you could also, and this is what I found super useful with Julia, is that because there's obviously a lot of computations happening inside such an atmospheric model. There's a lot of functionality that we need to use anyway. But the way how we've written this is that we basically expose all of this functionality directly to the user. So instead of saying, like, I don't know, I can compute my gradient somewhere down in the bottom of my model, then you get the output, and then you give the output to a PhD student, and the PhD student has to figure out again how to do the gradient. No. We do this differently. We basically try to expose all of the functionality directly. So if I call the spectral function here, it's exactly the spectral function that's also inside the model, transforming just from this grid point space that you can see here into spectral space. And if I then plot this, you could see this is what the land sea mask would look like in spectral space. And here's basically, you can just about see that there's some power in these like lower order modes, but this is basically exactly your triangle of the spherical harmonic. So you could basically just do the spectral analysis here. You could look at the spectral power. You could do any kind of other analysis that we have here. You could interpolate between different grids because guess what? We have these operators anyway in the model, and so you should also be able to use them. And so if I run this model now, I'm not quite sure whether I compiled this yet, so it's probably just currently just in time compiling it, so it might take a few seconds. Let's wait for that, and here you can see I just like put the output to true so that we can hopefully look at the netcdf file in a second and see what happened there. Yeah. Exactly. So now it's simulating. You see it's definitely much slower than it was before because guess what? We also have a third dimension now that we're simulating. And it will give us in a second basically a little bit back of what's just been simulated. That obviously doesn't tell us necessarily, like I'm used to these plots, so I'm kind of, it tells me a little bit, but we're definitely thinking about something a bit more like some kind of small feedback that you get directly after the simulation so that you know what happened. But often what I then do, and let me escape this here, is that let me get a new terminal here. I think we were in talks, Julia EO, no, where are we? 2024. And then what we just simulated was this one here. And so this is this NC-Vis viewer. I think it's a bit similar to what Francesco displayed yesterday for HDF5. And now we could, for example, look at humidity. This is now at the top of the atmosphere, so let's go maybe a bit further down. There's more humidity the further down you go. So let's say this is, I think, surface humidity. And now you could just press play and see, maybe let's give it another color map that looks a bit more like humidity. And so you can see how humidity is concentrated in the tropics and how this is moving around. You could then look at, and this is basically how I developed this model a lot, that I just look at, oh, what's happening here, what's simulating, that looks reasonable, that doesn't look reasonable, or there's something going on. This is, for example, vorticity at the lower levels, but you could also go higher up, and you can see how this simulation was working out. And basically, my dream for the future is to have a model that is as easy to use as this one, but that really can also do really high quality research by, for example, just putting like a neural network in, let it learn something, and be able to, it should basically be, and this is really I think where this is trying to get at, it should be as easy to use for, like, say, an undergrad or master student as it is for someone who does research. And if it's really easy to use, I also hope that it will really accelerate the research that we do, because if it's already hard for someone with a postdoc, with a PhD to do this kind of stuff, then guess what? You're not going to be the fastest at something if you can do it as an undergrad or as a master student. Thank you. Any questions? You can run it again if you want to.
Milan, thank you very much. What about the ocean?
Yeah, so
Do you have
Speedy Weather at the moment has this, it basically just prescribed SSTs at the moment. We have created, because we just thought like it would be nice to have it a bit more flexible. So it is a general interface where basically on every time step, it's just the ocean is just called, and at the moment the ocean model is a seasonal climatology model. So that basically just pulls a seasonal climatology from data and just steps forward in that sense. There are obviously like ideas to couple that to a real ocean model. It's definitely something that's on my to-do list, but it's not something that's super easy. Like, it's not something you do in a day. And so, yeah, I don't really know exactly where the whole coupling is going to go in the next years. Because I think there's already a lot on the to-do list if you think about putting neural networks in and let it learn something. And so I don't necessarily always, with this model, I don't necessarily want to go down the conventional way of model development. I deliberately want to skip some of the things that large teams have basically spent decades on solving for the individual models, that I feel like if I would do the same, I would still give the same talk in 20 years and wouldn't really give you necessarily an update. And I kind of want to try to go into very different directions and like basically use this as a starting point, but now go into like try to do things differently and see whether they actually bring you faster somewhere where this is something useful than the conventional modeling approaches are.
Okay. Thank you. Yeah, I also agree you should go different.
Thank you very much for your presentation. Just one comment. Have you done some comparison with traditional models with, I mean, very simplified implementations? Do they behave similarly or in a different way? Like, I don't know, like the WRF or something like this?
So if I got your question correctly, like, no, sorry, say it again. What was your question?
So what I mean is that you developed this from scratch,
yeah.
No? But there are already existing models that they are doing with the probably programming in other language and develop with longer periods like WRF.
Yes, WRF. Yeah.
Have you done any comparison on? I mean,
no.
try to run them in a simplified manner, like the one that you saw here, to see if they match, they don't match, what are the differences?
Yeah. So that is definitely something that at some point needs to be done. At the moment, I've been implementing a couple of these like test cases. They're like baroclinic instability test cases to see that the model is actually simulating the right thing. It does on those ones qualitatively, but I also don't want to like I don't know, spend a year on just like exactly like doing like a quantitative analysis compared to something else, because in the end I actually would like to go away from other existing models and directly want to reference it to data, so that you could, for example, say like I just press play here, I could run it for 100 years if I wanted to, and I would get, for example, some kind of climatology for, let's say, temperature over the Azores, and then would directly reference it to that data. And then ideally you could, in the similar way as like Chris described today, where you just basically plug in your network as like a correction term that takes care of everything that you don't know, that should obviously then learn directly from this data. And so, yes, of course, at some point we will like compare to other models, but I don't think this is at the moment the main focus of this work. Yeah. Great. Oh, well, that was not mine. It was just.
I could be VGMI.
Ah, you directly use this. Okay.
So just a quick note, this is the end of the lectures or the sessions, interactive sessions as such. And tomorrow we have the hackathons. However, tomorrow is not going to be streamed and it's not going to be recorded. There are private sessions here. So a big thank you to all of you. We had around 120 participants online. Thank you to all of you. I hope this was very useful. We will be placing these links to videos for each session on the repos, on our repo within each session, and you can always review these as many times as you need. We are going to give you certificates of participation. You need to give us a couple weeks for that. There will be a survey for participants, for speakers as well, for those who are here as well, but naturally for those who are online. So please answer to those, because those help us make better events. And please be in touch. We really see this as a long-term effort. Julio 25 will take place 6th to the 10th of January 2025. And so feel free to get in touch with us if you'd like to come here and participate in person. We'll also be hiring, so if you have interest in working with us, if these topics are of interest to you, you are of interest to us. So thank you very much to those who are online. Now we have a coffee break, and then we have the expert hour right here. It's also not recorded. And so this expert hour will be partially structured. So Francisco asked to come here and launch or remind you of a challenge that he has for all of us. So let's have coffee, and I'll see you in a few minutes. Thanks.